This is Geometry Lesson 3.5, Justifying Conclusions. Before we start this lesson, I need you to gather all of the note packets that you've been given so far. I need Chapter 1, Chapter 2, and Chapter 3 note packets all together with you because you're going to be using them as a resource throughout this whole lesson. I also need you to be prepared to hit pause frequently throughout the lesson. I won't necessarily tell you to pause, but I will ask you to go look things up and look for certain things within your note packets. So it's important that you're ready to pause things and interact with the video in that way during this lesson. This lesson is extremely important, and it really sets up our concept of proof and how they're working, and is really going to set the tone for the next few chapters that we study in geometry. So first of all, what is proof? Proof is a sequence of justified conclusions leading from what is given or known to a final conclusion. And we looked at that in the last lesson when we looked at solving an equation. I set it up in proof form. I didn't necessarily talk about it, but I had a column for conclusions, and that was the column in which we solved the equation. And then for each step that we followed within the solving of the equation, we then had a justification for each step. And that's what it's like with proof. Everything we do, we have to justify. Every answer that, or every conclusion that we draw has to be justified. And we justify with things like theorems, definitions, postulates, and properties. So to begin with, I would like you to have, like I said, pause the video and get all of those things with you. And then we'll start with the first set of examples. When you see something that's a given and a conclusion, I want you to change how you're thinking about that and think about the way we did things in Chapter 2 when everything was a conditional. So I want you to think of the given as your if statement and the conclusion as your then statement. Then what you're going to do is you're going to look for the theorems, the definitions, the postulates, the properties. We're going to look at those to see if there's anything that matches. So let's take this first one, given. If AB plus BC plus CD equals 24, the conclusion is that AB plus BC is less than 24. Now, this is probably not the easiest one to start with, but it still works. What I'd like you to do is turn to your 3-4 notes and find postulates of equality and inequality. And there's an equation to inequality property that says if A and B are positive numbers and A plus B equals C, then C is greater than A and C is greater than B. So basically what they're saying is the parts are smaller than the entire thing. So right here, all of the parts together make 24, so sum of the parts together is definitely going to have to be less than 24. So we would then want to write our justification for that piece as the equation to inequality property. Let's take a look at number 2. And I would like you to actually turn to your notes from 3-1, where we defined all the different types of angles. So I want you to think of the first part as the if statement. If I know that the measure of angle BAC is 99.995, so we know that it's less than 90, the conclusion I'm drawing is that angle BAC is an acute angle. And so if you stop the video and find your definition of all the angles, there is one particular type of angle that says the angle whose measure is greater than 0 and less than 90. And that happens to be an acute. So our justification for being able to draw that conclusion is definition of an acute angle. Feel free to draw in symbols when justifying these and abbreviate as well. You will see that I will abbreviate definition for DEF for definition, and I'll point out other ones too. In this next one, 3x plus 16 equals 46. We know that I can add a negative 16 to both sides, and if I do that, I then get 3x plus 30. So if you look at the notes from 3-5, we know that that's the addition property of equality. So that's our justification, addition property of equality, and that's how you can abbreviate that one. Let's take a look at number 13 here. I'm given that angle 1 and 3 are vertical angles. And the conclusion I'm drawing is that the measure of angle 1 equals the measure of angle 3. So what I need you to do is I'm actually going to direct you. I want you to go to lesson 3.3, and I want you to look for something that says, if I have vertical angles, then I know those vertical angles are equal. And if you look at it, if you look down on that page at the bottom, there's stuff about vertical angles. There's a definition of vertical angles, and there's a vertical angles theorem. You need to pick the one that says that I have two vertical angles, so therefore my measures are equal. And so in that situation, it's actually going to be the vertical angles theorem. Now, many of my students in the past have wanted to write the definition of vertical angles, but all the definition does is describe what vertical angles are. But the theorem, the vertical angles theorem, says that if I have vertical angles, then I know they are equal. Still drawing your attention to lesson 3.3 in your list of definitions, let's take a look at this number 14. The measure of angle OQA is equal to the measure of angle QV. And the conclusion that I'm drawing is that QA bisects an angle OQV. So we look at it, this angle is equal to this angle, and the conclusion as I'm drawing is that this ray is the bisector of this large angle. So if you go and look at your notes from 3.3 and look for something that talks about a bisector, a ray bisecting and making two equal angles, you will notice that the definition of an angle bisector does that. So when you're going through and you're trying to figure out what your justification can be, you really want to look for keywords. You got a ray bisecting, and in that definition, you see it says ray VR is an angle bisector of angle PVQ, if and only if. So we know that then we can have two equal angles. So clearly, I've got some keywords in my given and my conclusion that would lead me to find my justification of definition of an angle bisector. Let's continue on with number 15, 16, and 17. Here I'm given if 7 and 8 form a linear pair, the conclusion is that I want to draw this, that they're supplementary. So still sticking with 3.3 notes, I have a linear pair, so therefore my angles are supplementary. Look through that list and see if you can find anything about linear pairs and drawing conclusions that your angles would be supplementary. So if you look at it, you have a definition of linear pair and you have a linear pair theorem. You need to pick the one that talks about supplementary angles, and that would be the linear pair theorem. Okay, if you read that, if two angles form a linear pair, so that's my if, then they are supplementary. That's my then. My conclusion is my then, and it fits very nicely. Now, number 16, you don't have anything in your notes excuse me, in lesson 3.3, and actually happened in chapter 2 when we discussed triangles, but it says triangle JMH is equilateral. So if you go back and you think about what was an equilateral triangle, they said all the sides were equal. So the conclusion that was drawn here is that JM equaled MH, which equaled HJ. So clearly the given triangle JMH is an equilateral triangle, and the conclusion is that all sides are equal is really a descriptor, so we would be using definition of equilateral triangle. Number 17 also is another example where we didn't do it in chapter 3, we actually discussed it in chapter 2 or 1, where we talked about the center of a circle to the outside is equidistant for any point, from the center to any point on the circle is equidistant. So if I look at half circle C and I'm going from TC and CZ, I know that my distance has to be the same because it's a circle, but I know that because the definition of a circle says so. Before we work through this problem, I want to talk about what a proof is, how we set it up, and the method that we're going to be using to write a proof. So the first thing is, when you have a proof, you're going to be given information and you're going to be told what you need to prove. And it will be given to you somewhat like this: given, colon, and then what you're starting with, the information that you have, and then the last thing is the proof. What do you want to get to? So when you're doing a proof, you always know that we're going to have a series of steps with starting place and an ending spot. And in that series of steps, the first step is always your given, the last step is always your proof. I've set this up in a table format, and that's one way that you can go about working through your proofs. Oftentimes we'll do what's called two-column proofs, and that's how this one's set up. We'll talk more about paragraph proofs at a later time, but right now I'm just going to talk about the two-column form. So your first column is always your conclusions that you have, and the second column is always your justifications. So the first step is my given, and you can see here I typed it in and wrote given. So then what I do is I go to my next step and I say, what information can I conclude from what I was given? I know that I can add 17 to both sides and get 5x equals 40. So the reason I can do that is because of the addition property of equality. We talked about that in the last lesson. Now I know that I need to get to x equals 8, and I can get there by dividing both sides by 5, or remember, that's the same as multiplying by 1/5, and that's the multiplication property of equality, which would take me to the x equals 8. So first step is always your given, last step is always your proof statement. So on a test, if you're ever given a proof, you know you can fill in those two things, and you know your justification for the first one is always the given. You have 2 more proofs in your note packet, and we will do those together in class. So this concludes lesson 3.5.